the polymer models which are applicable to short fiber reinforced plastic parts. We will talk a bit about the failure description, which is rather unique and complex if you want to deal with a realistic description of failure for short fibers. And then we will turn to the state-of-the-art solutions as we offer them in DIGIMAT. So this will concern reverse engineering strategy a little bit, material exchange platform. What is that? It's the MX module that we have in DIGIMAT software. We will look into the interfaces that we offer, some small insight into mapping technology, and then I will finish with talking about a hybrid solution method, the new solution method which is available with the current release of DIGIMAT 4.2.1. And then we will end with some future outlook. So this will be our R&D topic. So this concerns lifetime prediction for short fiber reinforced plastic parts, a very active area that we currently work on. Okay, so let's start ahead with the challenge for short fiber reinforcement. And what we look here on this slide is basically the situation that you're in your everyday application. So basically you perform injection molding for your parts in practical application, and most probably you will have access to injection molding simulation. And basically what injection molding simulation is capable of is the prediction of the orientation of short fibers on the part. And here we look at some let's say easy example, but this example contains everything that can happen in a real part as well. So I like to start a little movie. So let's just take a look at the injection molding simulation, the filling simulation itself. And you can see that in this plate we have reduced quite the complex situation of a three-dimensional part to two dimensions. So the plate is filled with the melt, and then we have introduced some nice holes into the plate to enforce what we would call a flow line after the first holes. And then when the filling completes of the plate, we enforce another very typical and critical situation, which is the occurrence of a static weld line in the part. So all this is happening in the filling of the part, and now the question is, how is this influencing the fiber orientation? So if we just go through the fiber orientation as we see it here in two dimensions on this slide, step by step, we start with a fully aligned flow going into the plate, so we can nicely see that we have a very large amount of fiber alignment in the beginning, and then we encounter the holes which we put in the plate. And basically after the holes we have the situation that some flow lines appear, and again we see the flow lines basically in the microstructure, in the arrangement of the short fibers. And as we go along we also see the static weld lines in contrary to the flow lines, which are basically highly aligned fiber arrangements turned in a different direction in space. The weld lines themselves are represented here by some three-dimensional stochastic distribution of fibers. So it's quite some nice example. We find very typical situations. And now we want to start a little bit step by step looking into the example deeper. And the next question would be, of course, if I want to start a simulation on such a part or submodel of the part, of course I need material properties. And what are the typical sources of material properties if we look into practical applications? So first would be to have some ISO 527 type of dumbbell, which is directly injection molded, and of course which can be used for measuring the material properties of a composite material of a short fiber reinforced plastics. Now, this is quite the simple approach, I would say. Of course it's quick, it's cheap, but it gives you some average material data for your composite. If you like, so what you don't get here is any idea about the anisotropy of your material properties. So in principle, what you need to know is what are your material properties if you look along the short fibers, what are your properties if you look perpendicularly or in any other angle with respect to some, in the best case, perfect fiber alignment. And this is exactly what you test if you take the second approach that we look on this slide here. So of course you can injection mold a plate, quite similar to what I have shown on the first slide, and then it's a plate which is dominated by the fully aligned flow. So we have highly oriented fibers. I mean, in reality, they are not all perfectly oriented, but you will encounter some situation which is called the skin core effect. So you will have a layered microstructure with some perpendicular fiber arrangement in the middle of the plate, and this skin and core relation is thicker or thinner or whatever. That quite depends on the material itself, but this is the basic situation. And what you can do then with such a plate is you cut out dumble with respect to the main fiber alignment direction. So that would, for example, be 0, 30 degree, 45 degree, 60 degree, 90 degree, so on and so forth. And from this you can get a set of curves of material measurements. And if we look at these measurements, which you can get out of such an experimental setup, you see that if you measure along the fiber direction, the material property is governed by a high stiffness of the material and some brittle failure. And then as a rule of thumb, you can say if you go towards 90 degree angle with respect to the fiber alignment, then of course stiffness is lower because you go more and more perpendicular to the fibers themselves, and the failure behavior turns more to a ductile behavior of the material. And so this is exactly the challenging situation, because all these different curves that we look at here on the slides must go into one material model in principle. So this leads us to the question, how are the material properties from these measurements used in simulation in a practical approach? And if you go to companies these days, some will want to tackle this in some anisotropic material model formulation, but what you quite often find is that there is some straightforward approach, which of course is nice because it's very quick. So you could take, for example, your ISO 527 specimen measurement, and I mean, we know quite fairly about the average orientation in such a dumble. So we know the orientation tensor, which represents the fiber alignment. But even with that knowledge, you just take the material properties and you scale by a factor, and mostly in the companies there is some history to the scaling factor. So basically it comes from comparison to force displacement curves, which are deduced experimentally, and then the scaling factor from the simulation is applied such that the experimental value is fitted best. So basically it's a matter of experience what kind of factor to take, and the typical factors are ranging from 0.6 to 0.8. So it's an assumption. The factor is by no way fixed. No one can tell which one's the correct one. And of course you could take the more precise material measurements now, so the dumbbells cut off of the injection molded plate, and do the same approach, but rely then with respect to the 0 degree dumbbell properties and deduce your material properties from that. But again, here the scaling factor is unknown. So, but in principle, the approach, of course, can be done. And what you do is you put up some nonlinear material model, so plasticity in your model, but it's isotropic. And what you can do also, of course, is you take all the measurements from the injection molded plate. So you have experimentally measured your anisotropy, your dependency on the angle with respect to the fibers. And now on all the curves you have measured, you perform some reverse engineering of some anisotropic material model, and even here you can include the skin core effect, as we have discussed it before, in terms of putting up a real multi-layer RVE. So RVE stands for representative volume element. So basically, you put up a microstructure in your composite material, which is a real multi-layer, and so this way you can deduce a highly high-quality anisotropic nonlinear material model. And actually, the latter approach for the anisotropic is what we do in DIGIMAT, and the isotropic is the brute force approach. And I just want to take you on a small journey for the plate, which we have seen in the first slide, and I just ask for a small submodel. So for this flow line situation, what would be now the effect of the anisotropic material model versus the isotropic material model as coming from some experimental measurements? And so what we will do is that we take this submodel and take a very typical situation. So just imagine you would injection mold a plate, you leave a hole, and this hole you use to just screw the plate to some underlying second plate. So basically you just fix your part to the environment where it should perform, and this was some injection molded part. And to reduce complexity here a little bit, so we used some simple replacement boundary conditions to describe all that. So basically what we have around the hole is some displacement which we apply, and then the plate is fixed by some frictionless support boundary. So this we use, and then we use for the material properties some nice feature which you can find in DIGIMAT MF module. It's that you predict really based on some microscopic material model, a nonlinear stress strain curve, and then if you have one curve, you can export this curve into some material card which is isotropic and ready to use with any FEA solver. So basically what we did here is that we fixed the underlying microstructure in the same material, and for this fixed microstructure, we exported material properties. And what we did now is that we computed the material curves for our composite material, and this by varying the fiber orientation. That is what we look at here on this slide. So basically for the material, which is polyamide 6, reinforced with 30% of glass fibers, we have started to deduce a stress strain curve along fiber direction. We see this blue curve, which is the stress strain curve for the representative fiber orientation, which we find in some ISO dumbbell. Then we see in the dotted orange curve, the higher one, some measurement for random 2D orientation, and then we have the weakest curve if we do tensile testing perpendicular to perfect fiber orientation, which is the lowest curve. So in principle, this is the material behavior that you can encounter locally anywhere in your part, depending on the fiber orientation. And so what we did now here is that we looked at the global force response of the fitting around the screw. And here you see three different curves. The blue one is for some isotropic material, which refers to the directly measured ISO 527 dumbbell. Then you see it's a very stiff response, much stiffer than what you would expect. So the green curve then is an improvement on this in terms of saying, okay, let's further use some isotropic material model, but we know that in the plate probably we have rather a random 2D orientation, which we apply the load perpendicular onto, and the red curve is referring to a full computation of an anisotropic model, and in the lower right bottom you see the fiber orientations that have been locally taken into account with that material model. And now we can quite fairly understand why the stiffnesses of these global force responses are so different. So we apply loading in Z direction, basically. And if we compare now the fiber alignment to the loading direction, what we find if we say, okay, let's just take the value of some isodumble, is basically that we align the fibers in the load direction, and this is of course the stiffest possible material properties which we can assume, and this is absolutely not what we find in the plate if we look at the fiber alignment with respect to the loading direction. And so things improve a little bit if we go to the two-dimensional fiber orientation. So we see that we reduce really the maximum force from 100% if we scale it for the isodumble to 36% for the 2D arrangement, but still we are a little bit far away from what we find for the realistic case where we really compute anisotropically the behavior. And so with respect to the isodumble, what we find is that the red curve lies at 22%, and it's even weaker than the 2D arrangement. The reason is that really what we find in the plate is like pressing perpendicular onto the fibers, and this, as we saw before in the slide showing the material behavior, is the weakest material behavior that you can imagine. So it shows quite well that even for the global force response, it's highly dependent on the gas that you put into some isotropic model, and it quite well can be predicted if you use an exact anisotropic model. Now on the following slides, we just took the two-dimensional isotropic model and compared it to the fully anisotropic model, and the question is not what is happening to the global results, but what will happen to the local results. And how is the local result now reflecting the fiber alignment in your part? And so first thing we can look at is, for example, the deformation in X direction. And if you look on the left side of the slide, you see for the isotropic case, you have some symmetric behavior of the deformation in X, and this is natural because, of course, it's dominated by the geometry of the plate if the material model is isotropic. So it's easy to understand, but if we now switch to some anisotropic model, indeed we see that the deformation in X direction reflects the flow lines as we find them in the fiber alignment. So the underlying microstructure really becomes visible in the results that we compute for our plate. And this is also the case when we go for maximum principal stress as a result. So again, we go from symmetric result fields to asymmetric, which is reflecting the fiber orientations, but also the level of stresses that we find are hugely different if we compare the anisotropic and the isotropic model. Again, we can look as a local result at the plastic strain that we find in the composite material, and it's the same story, the symmetric result for the isotropic and some anisotropic asymmetric result for the anisotropic material model. So all these indicates quite well how the underlying microstructure influences global results as well as local results, and I want to finish with that quite artificial but educational example in discussing what would happen if we take the second submodel where we actually have a static weld line predicted in the microstructure. And indeed, what you see for this tensile bar in the lower left bottom is that with a fully coupled simulation to an anisotropic material model, you find the weld line in your results. So in the weld line where you have randomly 3D oriented short fibers, you see the largest accumulated plastic strain. So basically, you predict the breakage in the weld line, even though this is only part of the weld line behavior, which is reflected in the microstructure here, but it's still, weld line is the weakest. It's the weakest spot in the part, and this is predicted already by just taking into account short fiber orientations. And of course, with some isotropic model, you would see just a homogeneous stress state or strains in the tensile bar, so no way of predicting a weld line such as we look at here in these pictures. Okay, so one could say this is more like a very simple example, but now let's turn to some experimental case studies showing what our customers do with the software. And first one here is from Schneider Electric, and basically what they did is exactly the same that I showed you before for the simple example. They compare the simulation for material properties, isotropic material model derived from some injection molded plate, and basically this is the black curves that we look at. The blue curve is then some simulation using a DIGIMAT material model, so fully anisotropic, and the red curve is the experimental curves, and they have compared that for some glass fiber filling of 20% and some fiber filling of 50%. And it's very interesting what we see here. First, for the 20% fiber filling, we see again this about 85% reduction of the prediction of the force displacement curve. If we compare the black and the blue curve on the right, on the left side, and this is about what we saw in the other example before also. But now we see that the blue curve really nicely matches with the experiment. And then if we increase the glass fiber amount, we see all of a sudden the factor between the black curve and the blue curve increases. So 120% difference between the curves, and the blue DIGIMAT curve again matches the red experimental curve very nicely. So what can we deduce from these results? It's basically that even if you would use some isotropic model and a scaling factor, the scaling factor is dependent on the glass fiber filling. So by no way, even for the same amount of glass fiber, you know what factor to use. But even if you have a realistic factor for 20%, you cannot use this factor for 50%. But really, one by one, basically, you only fit your simulation to the experimental results. But this is by no way predictive. Whereas with using the DIGIMAT material model, so full anisotropic behavior of the material, it's predictive and matches the experiment quite well. And basically, the same study has been performed here in this study, which was a combined study of Taikona and Arvin Meritor concerning some plastic part from a sunroof. And here what they investigated was scaling factor, of course, what scaling factor to use. And then the fully anisotropic model, that would be the black curve here in the graphs, and it's compared again to experimental testing. And now testing has been varied. So one test condition was that a global load on the part was applied, whereas in the second, and this is on the right side of the slide here, case, a more local loading was applied. So what they found is that indeed, if you use some isotropic model, it depends what kind of scaling factor you need to come close to your experiment. It depends on the kind of loading that you apply on the part. Whereas again, with the DIGIMAT model, it's predictive. So here, just some glass fiber filling of 20% was the underlying condition of the anisotropic material model, and the material model was high quality, and the results in both cases matched the experiment very, very well. And so this was for some quasi-static testing, and the last experimental case study I want to show you is from L&L Products Europe. And this concerns explicit simulation. So in explicit, of course, you want to take a look at the correct failure behavior, and the correct failure behavior of your part is of course highly dependent from the correct local stresses, or the stress fields that you compute on your part. And what they have done here is again the comparison between isotropic and anisotropic. Again, in the isotropic approach, there were deviations from the experimental measurements for the global response of the part. But what is even more critical is that with the isotropic model, they predicted the failure behavior of the part in the wrong way. So the failure was really happening in the wrong mechanism in the part. And by switching to the fully anisotropic DIGIMAT model, they succeeded in predicting a correct failure behavior, as they could see it from high-speed cameras in the dynamic scenario, testing scenario for this part. So many reasons why one should use the anisotropic material description. And so let's turn a little bit to material modeling. Material modeling is exactly the expertise of our company, of Extreme Engineering. And here we will take a look a little bit into mean field homogenization, then into the polymer models, and then the failure description that we offer. So let's start with mean field homogenization. What is it really that we call a DIGIMAT material model? And you can actually quite simplify that for short fiber reinforced plastics in terms that we basically separate our composite material, so the full polymer as it comes along, into two materials. So one is matrix material, that is what bears the polymer properties, and the other one is the short fibers which we embed into this material matrix. So basically two different material models, and what we do is that we use then nonlinear material models to describe the polymer matrix, and you will see later on what kind of possibilities we offer here. The glass fibers themselves, they are quite simple. So here basically we take some linear elastic isotropic material properties which we associate to the glass fibers. And so we take the composite apart, and if you do that, of course, the question arises, how does the microstructure look like? So the microstructure in our material description is really put up by some matrix background and then inclusions embedded in the background. And all this is based on some Eshelby type of approach. And basically what you have is you embed some ellipsoid in the matrix, and this ellipsoid has an aspect ratio. So in brief, that means we give some aspect ratio which describes the ellipsoidal shape then of the short fiber, and this is a very fair assumption for short fibers as it turned out from our experience. So aspect ratio is about let's say 18 to 25 or something, describing a short fiber. And then the second information that we put in is the orientation of the fiber, and here it becomes complex because orientation is usually given in terms of some orientation tensor. And the orientation tensor is exactly what is predicted by the injection molding simulation software. So what do we do with that? As I said, the microstructure is the complex part. So here is some depiction of what we do, starting on the microscopic level in the middle of the slide on top. So basically here it's some composite material with fibers. Fibers are in black and have different spatial orientations, and then even you have the ellipsoids, the white ones, which pose some second type of inclusion again in different orientations. And what we do is that we decompose this complex situation in the first step on the microscopic level, and we collect together in classes all the fibers with the same alignment. And basically what we do is for these subcomposites, and we call them pseudo grains, so each class with the same alignment is called a pseudo grain. We compute some homogenization method, so what we take is Mori-Tanaka theory, and per pseudograin level, then we get our material properties, and then we take from this pseudograin level a second averaging step, bringing us to the macroscopic level where we have the full property of the composite material. And so this is the one-by-one approach as one could depict it, but of course it's hardcore mathematics what's behind that. So let's put it in some different picture. And let's start this time from the orientation tensor, because orientation tensor, as I said, is what we get out of the injection molding software. So starting with the orientation tensor, what we do is that we go to the orientation distribution function. And basically, to deduce the orientation distribution function is exactly to go to the pseudograin levels and to separate the fibers in classes of different alignment in space. And for these pseudograins then, per pseudograin, as I said, we perform Mori-Tanaka homogenization. So here we compute basically from the matrix properties and the fiber properties for these perfectly aligned fibers the correct stresses and strains. And so per pseudo grain, all these stresses are known. And this is with respect, of course, to some global load on this complex structure. So if the load is perpendicular to the fibers, of course, stresses are low. If it's a long fiber, stresses are high. So on the pseudo-grain level, you basically get some stress distribution. And then in the final step, bringing us to the macroscopic composite level, we do some void averaging between all these stresses. So basically what is left is that on the composite level, we have one mean average value for the stress of the composite deduced from the pseudo-grain level. And so the concept of pseudo-grain level and computing stresses and strains there is very important for the theory and technology behind our DIGIMAT models. And this is what we use later on also in the failure description. So please keep it in mind for the later slides. So for now, what we can take with us is that we have this technology here, and basically what you can do is you just give the input for the material matrix, the filler properties. You set the microstructure, you say what kind of shape does your filler have, you perform your homogenization, and what you get out is material properties dependent on fiber orientation. And this is exactly what a DIGIMAT material model is. And all this technology you will find in our module DIGIMAT MF, and MF stands for Mean Field Homogenization Theory. So what is available? Some quick overview over the material properties that you can set for your composite. So starting, of course, with linear elasticity, going to elastoplasticity as nonlinear behavior, we offer you plastic polymer models which are orientation dependent. So you look here at graphs as a function of the orientation tensor, so basically of the orientation of the short fibers. So these are our basic mechanical models, and then you can enhance them by introducing the strain rate dependencies. So strain rate dependent models would be viscoelastic material properties or elasto-viscoplastic material properties, and here we differentiate in dynamic scenarios where you have very high strain rates, so more like crash scenario or crash type of application, and this we have in the software for a long time. And what we now turn to is a better description of creep, so very low strain rates which we describe, and you will see in the upcoming version of the software that we quite well differentiate between these two different scenarios, and there are different theories behind the homogenization that we perform for either dynamic or creep situation. But this is available, and so let's look at the next dependency that we can introduce. So that would be temperature dependency, and the simplest form of temperature dependency is for thermoelastic material properties, and here we can set, for example, the Young's modulus as a function of the temperature, as you can see it on the right side of the slide. And then we can enhance that again, so we can go to thermoelastoplastic material model, for example, and one base of our temperature-dependent material model here is that all the parameters of the material model can be temperature-dependent. So here in this model, already the Young's modulus, the yield stress, and all the describing parameters of the hardening of the curve are fully dependent on the temperature, as you can see it here in the graphs on the right side. And now you can even go further and say, okay, let's combine temperature and strain rate dependency. So we're looking here at some thermo-elasto-viscoplastic material model, and all this kind of technology is available in DIGIMAT. And it's, of course, it's highly complex with to work with such models, but it's all available in principle for your simulations. So you see there is a large background for the material properties, so for stiffness prediction, and let's now turn to failure. And as I said, failure is also located on the pseudograin level, if you like, in DIGIMAT. We have the classic failure, which is coming from the macroscopic level, but it's very well known that this is only a very coarse assumption if you want to deal with failure for short fiber reinforcement. So for short fibers, in principle, what you need is to know how the failure behaves if the fiber is oriented in a special angle with respect to the load direction. And exactly this you can compute if you go down to the pseudograin level. And this is what we do in the so-called first pseudograin failure model that we offer in DIGIMAT. So FPGF, this is the abbreviation for it, FPGF overcomes the limitation of the void averaging step. So this is the final step that we perform in the homogenization approach, which brings us to the macroscopic level. FPGF moves the failure prediction really to the pseudograin level below. And so in each pseudograin, a state similar to classical laminates is found. So each pseudograin, of course, contains fibers which are fully aligned. And here you can use failure indicators as you're familiar with from classical laminate theory. And these we use on the pseudograin level, but to predict the failure of the composite itself. So for example, Sci-Hill 3D failure for the composite is predicted for each pseudograin. And what we have is that the grains then fail one by one. So for example, here in the stress distribution, the pseudograin with the highest stress would fail, whereas all the other pseudograins are sufficiently low in the stress level and they would not fail. And what you have even an influence now of failure of this pseudograin on the stiffness of the nonlinear part of the elastoplastic curve, as you see it on the right side of the slide. So reducing the stiffness of the curve as we go along, and the pseudograin fail one by one. And then in this model, you set a maximum amount of pseudograins to fail until the full composite has failed. But the trick is really to go down to the pseudograin level and deduce the failure from there. And so if you do so this means that you really take into account the stress history per pseudograin. And of course, if you think about all the possible orientations in three-dimensional space, this is a lot of information that we have to compute. If we do that for one representative volume element, so on one integration point, let's say on the material point itself, we can quite nicely show that now we are able to reproduce the failure as it should be. So if we go along fibers, we have high stiffness with brittle type of material behavior, and if we then turn perpendicular to the fibers, we have material behavior which is more governed by low stiffness and a ductile type of material behavior. This we can nicely show, but as a matter of fact, we can only compute that on the material point because it involves so many computations per pseudograin that we have to do. And what we do to bring this kind of failure description to the applied simulation level for full parts, where we apply the failure on each integration point, is that we use a macroscopic failure envelope as computed by DIGIMAT-MF, so on the integration point level, and use it then on the macroscopic results on our model. And this is called the hybrid failure indicator. And the idea, the principal idea of the hybrid is to deduce only macroscopic properties if you go for coupled analysis. I will talk about this solution method, which is quite new in our software, later on in a few slides also. So this is a very highly precise and physical failure behavior that we find here with our material models. And so in principle, now we have understood what we have in terms of complexity and theory behind our material models, and let's turn now a little bit to the everyday usage of these material models. And this is the state-of-the-art solutions as we offer them in our modeling platform. And DIGIMAT contains in its platform of different modules. So DIGIMAT MF we have already seen. DIGIMAT MF is the base module which embeds all the theory I have talked about in one easy to use module, but it's enhanced by some module called DIGIMAT MX. Then our interface module, DIGIMAT CAE, and some mapping module. And I just want to lead you a little bit one by one through these additional modules. So DIGIMAT MX is used for the parametrization of DIGIMAT models. You set up high quality material models using DIGIMAT MF, but then you need, of course, some type of data management. So you want to parameterize your model, so you want to compare to experimental data, you need fitting routines and all that. This is what we call reverse engineering procedure. And this is exactly what you find in DIGIMAT MX. So DIGIMAT MX is a database to start with, where you, in a very consistent way, store your experimental data, your DIGIMAT material models, and then you can perform also in that environment some reverse engineering procedure guided by some nice and easy to use GUI tool, which leads you to a calibrated DIGIMAT material model based on your experimental data that you gave. And so this model, again, you store in your database, and so it's ready to be used and to be shared. And sharing is exactly the second idea of DIGIMAT MX. So MX stands really for Material Exchange Platform. And Material Exchange is now the exchange of material models for DIGIMAT between some material expert and some end user of the material card. Because, I mean, you have heard a lot now about the theory behind these DIGIMAT models, and then reverse engineering is an art for itself. So you really need someone who has all these expertise to put up a high quality material model. And quite frequently what you find is that these experts are material suppliers themselves. So in DIGIMAT MX you will find a database which contains of public data, and these public data are already entries which are readily given by material suppliers using DIGIMAT. Then, in addition, you can put your own DIGIMAT models into the database and now share it between you and all the other users of DIGIMAT in your company, and all these sharing is controlled by privileges, setting user rights and group rights and so on. And it's enhanced by some encryption technology. So if you imagine a material supplier wants to share his DIGIMAT model with you, of course it's a lot of knowledge in this model, and he wants to be safe about the intellectual property behind this material model, and then we can encrypt the model. And this way, material suppliers and application engineers exchange encrypted DIGIMAT material models, so the application engineer uses basically the DIGIMAT model as a black box. And all this technology I have talked about you find in the DIGIMAT MX. And so how to use the DIGIMAT model, this you would take the DIGIMAT CAE module for, and basically what's behind that is in terms of injection molding, we can interface with all big injection molding codes on the market, so Moldflow, Sigma, Softmold X3D, 3D TIM and RAM 3D, and so on. And on the FEA solver side, we really cover everything that's there, basically, so Abacus, Altair software, and so on and so forth. And you put together your coupled analysis in this module, and then you run via user subroutine your DIGIMAT material behavior in your FE analysis, and the DIGIMAT subroutine automatically takes into account the fiber orientations as predicted by the injection molding code. So, of course, this is not as straightforward as I just mentioned, because usually what you find on the injection molding side is that you have a different mesh from what you have on the structural FEA side, and this means that we need to have some mapping tool, and of course we have that in our simulation platform, and you can quite nicely map tensorial or scalar data from one mesh to the other, and even control the quality of your mapping. So it's very robust, and it's a very important stepping stone in the overall workflow. So this overall workflow is available, and now let's virtually start our solution. And first, what we would do if we fully couple our DIGIMAT material model in the FEA is that what we call a micro solution method. So this means that we perform the full homogenization method at each integration point and time of our analysis. And what's behind it is, of course, the on the material level, the composite model that I talked about. Then you go to the element level, and per integration point, you read in some orientation tensor as predicted by the injection molding software and then mapped onto the structural mesh. Based on this, you compute the material, the local material property, and then on the macroscopic level, you get your stresses and strains as a field based on these material properties as predicted. And so this is the full approach, but of course it's demanding because at each integration point and time of your analysis, you have to run the homogenization routine via the user subroutine. And so this approach has its limits, and the limits are basically there when you try to compute something using an explicit solver. So here we encountered in the past a huge increase of CPU time, and if you look at explicit applications, you will find different levels. So starting with the level of the integration point, going to a dumble level where you basically reproduce a dumble experimental measurements. But what you really want to do is, of course, to go for dynamic scenarios on the part assembly level. And this can take you, if you use some explicit solver, and for example, the model we look on the left side of the slide here, up to 9 days. And this is, of course, critical in terms of CPU involvement. And the dream for the future, of course, is to go for full car crash, which includes injection molded plastic parts in the full assembly of a car. So system level computation, really. And so what we find is that the accurate method, which is called the micro solution, has its limits on the part assembly level, definitely. And what we have done is that with the 4.2.1 available version of our software, we have introduced some solution method which we call hybrid mesh method, and which is more approximate and which takes into account material properties on the microscopic level only. And this is now very successful in reducing the computational time and also gives very good results. And I just want to explain you a little bit about this hybrid solution method because it's very important. So as I said, hybrid means basically not a change toward DIGIMAT material models, but a change in the internal solution procedures. So we take our material model as it is, so micro and everything I told you, and then we reverse engineer a good approximation to the exact micro solution on the macroscopic level. And so this means that all the details of the per phase results and everything that you can get with micro, so this looking deeply into the stresses of the material matrix, for example, this is skipped. So we reduce the amount of information that we exchange, and this way we speed up our CPU of the computation. This method is available for elastic material properties, for elastoplastic material model, and elastoviscoplastic material model for now. And so what can we expect from that? And here is some example from the dumble level. So what we see is that the hybrid solution to start with is really fully anisotropic. So we nicely see for such a dumble cut out of a plate the skin core effect. It's covered very well. And we get high quality results if we compare the results to the exact micro approach. So this is true for the global response here, so the stress time curve. And if we look now at the CPU time to compute a dumble with micro, took us 1 hour 36 minutes, whereas with the new hybrid approach, it only takes 2.5 minutes. So it's a really vast reduction of CPU time. So great success in this case, and so let's move to the part assembly level. And here we see Again, very high quality results, so it's a perfect superposition of the force response that we compute by the micro method and the new hybrid method. If we look on the right side of the slide, we see a comparison of the local stress field, von Mises stress in this case, and you see that the stress field is identical between the micro and the hybrid method. And if we now look at the CPU time, this was exactly the example where I said it takes 9 days to compute. It reduces to 1 day, and the trick behind is even that the 9 days we're using 3 processors, whereas the run with the new hybrid method only uses 1 processor. So in principle, if you have the number of licenses, you can, instead of investigating 1 design in 9 days, you can take 3 variants of your design and compute all them parallel in 1 day. And of course, here we are really now back into the regime where you can work productively with the anisotropic material model. So hybrid solution method, just to summarize a bit the benefits of this new technology in our software. It's a great speed up, so at least a factor of 20 can be expected as a speed up for explicit analysis. This is true for elastoplastic and elastoviscoplastic materials. We have observed a large increase in robustness, and this is, let's say, by definition really, because all the homogenization steps, as I told you, are skipped, so all convergent trouble that might be located on that level is circumvented with a new solution technique. And talking about failure, hybrid failure is a part of the hybrid solution. And so the real physical behavior of the failure from brittle to ductile and so on is state-of-the-art FPGF technology in the hybrid solution method. And this is really what you need if you want to go for physical description of failure for short fiber reinforced plastics. And here we even move along currently that we make the hybrid failure available in combination with the microscopic and more precise prediction of the stresses and strains. So this is then micro solution plus hybrid type of failure indicator. Okay, so this is then coming to the end. Our last topic will be an R&D topic, so a very hot topic at Extreme Engineering. This is about lifetime prediction of short fiber reinforced plastic parts. So lifetime prediction, of course, is a very hot topic if you look on the market, and if we take the classical approach to it, what you basically do is you have some stress strain curves, so stiffness measurement of your material properties on one side, so this is on the left side of the slide, and for the fatigue properties, it's in some Wöhler type of measurement, so SN curves are measured, and both types of measurements go into simulation software. So stiffness goes into the prediction of the stresses using some standard FEA solver. So it's linear elastic computation used here. And these stresses, which are computed, go as a stress field into some lifetime prediction fatigue software. And this software then relies on the SN curves to predict then the lifetime of the part. So all this is fairly easy. Well, it's not easy, but it's straightforward and available in a workflow. If you go for methods, so isotropic material models basically behind. If you then want to go for short fiber reinforced plastics, as we have seen in all the presentation, it's anisotropic. So what changes in this approach if you move to anisotropic? And first thing that changes is the left side of all this, and we have to add the process simulation, so the prediction of the orientation of the fibers to our overall scheme. So we have 3 simulation softwares now involved. One is the injection molding on the bottom. One is the prediction of the performance of the part, the structural performance, which is the standard FEA, and then, of course, lifetime prediction by the fatigue code. And what we have on the left side is basically the workflow, which I have talked about on the previous slide. So it concerns the mapping of the fiber orientations, taking into account high-quality anisotropic material model, and all that goes into the FEA solver. So in principle, the predicted stresses from this approach are now accurate and based on anisotropic material properties. But what is lacking is on the right side, of course, that the lifetime prediction and the F and the Wöhler curves are also dependent on the anisotropy induced through the fibers in the material. And so what you need is anisotropic SN curves for high cycle fatigue. And this is exactly what we have in our software today. We base it, again, on the pseudo-grain approach. It's valid for a two-phase composite material, which is linear elastic. And basically what you input is 3 experimental SN curves, and what you get out is a prediction of the SN curve for different orientations. So again, we set different microstructures by orientation tensor or perfectly aligned fibers, and for different loading conditions. So it's exactly the same approach that we have for the stiffness now for the SN curves. What's behind it is of course, again, a complex material model, and the objective of this material model is to predict the maximum number of cycles before failure of the composite material. The method that we use is that for one load cycle, we use Mori-Tanaka homogenization to compute the stress evolution in the representative volume element. And then we compute the failure of one pseudo-grain. So for fully aligned fibers based on a Tsai-Hill 2D, it's 3D for the upcoming software failure indicator. And then the failure of the composite overall pseudo-grains is basically a weight sum over this failure of each pseudo-grain. And so this is then taking into account for any orientation and any loading condition. So that's the model behind. And you apply this model by reverse engineering to the input SN curves that I mentioned. So basically, again, you would injection mold a plate with aligned fibers. Then you cut out in different angles, and for each different angle, you have an SN curve. And then you reverse engineer the failure behavior as given by the model on the previous slide to your SN curve. So in this picture here, it would be the violet and the gray curve, so input 1, input 2. And based on that, you parameterize your material model, and then you can predict SN curves for any unknown fiber orientation. And this can be done with very high accuracy, and it's implemented in the software. So for the user, it's quite easy to use, I would say. You basically, as a workflow in DIGIMAT MF, you define your 3 experimental SN curves for the fatigue failure indicator, which we have in there. You define a loading, and then the reverse engineering procedure that I mentioned is really internal in the software. You don't have to take care about it. It just happens, and then it predicts the SN curve for the orientation that you have given in DIGIMAT MF. And so this is available with the current software. And this is the base for new interfaces to come, and they will come with upcoming versions of our software, and it completes the right side of our schematic here. So exactly as the left side, we start from processing simulation, and we map the predicted fiber orientations on the structural mesh. We then take the anisotropic model that we have for the Wöhler curves per integration point based on the local fiber orientation, and this we feed into the fatigue code. And of course, this is a collaborative effort, so collaborations are put up with LMS, ENCODE, and FEMFAT fatigue software developers, and this is ongoing development on our side. And what we have today is for the LMS Virtual Lab code, a beta version. So if you're interested in that topic, we will be happy to join in a project to validate what we have here. Okay, so this brings me to the end of my presentation, and let me just quickly summarize what we have seen today. So for short fiber reinforced plastic parts, DIGIMAT offers high-quality anisotropic nonlinear material models, and these models contain, of course, a good description of stiffness and failure. They include strain rate and temperature dependency. With these models, you can use DIGIMAT to bridge the gap between the injection molding simulation and the influence of the fiber orientation on the final performance of the part. So we have some efficient workflow in place for everything you need to deal with that situation, and it yields in high quality results. So this we know from our experience. As an R&D and future topic, DIGIMAT moves towards a realistic lifetime prediction for short fiber reinforced plastic parts. And as you saw, direct interfaces for lifetime prediction software will be established in the upcoming version of DIGIMAT. So thanks a lot for your attention, and I'll be